Here's a simple way to set the stage. A classical computer, laptop, phone, server, stores information as bits that are either a 0 or a 1. Quantum computing is different. It stores information in qubits, which can be 0, 1, or a blend of both at the same time. That single shift is the headline. It's not faster chips doing the same old thing. It's a new kind of logic built on the rules of quantum physics. Think of a bit as a coin that's landed, heads or tails. A qubit is like a coin still spinning. While it spins, it carries the possibility of both outcomes at once. And when several qubits are connected, entangled, they behave like a set of synchronized spinning coins. Touching one influences the entire group's pattern. That image isn't perfect, but it gives a feel for what's special. Why care about this? Because many important problems are less about crunching through steps and more about navigating massive possibility spaces, molecules with countless electron interactions, supply chains with a dizzying number of routes, cryptographic keys with astronomical combinations. Qubits let a machine set up and explore many possibilities at once and, crucially, use interference to nudge the system toward useful answers. So what's the catch? Reality is noisy. Qubits are delicate. The same environment that makes a chip exist also pokes and jiggles those quantum states. Without protection, errors creep in quickly. Quantum error correction, the art of protecting fragile quantum information, is the difference between a lab demo and a practical machine. Let that sink in for a moment. Two things are true at once. Quantum computing opens doors to new classes of problem solving, and quantum error correction is the price of admission. Now, the mental model. With one qubit, picture a spinning coin. With two qubits, picture two coins spinning, but tied together with invisible string so their spins are linked. With a handful of these linked coins, a quantum computer sets up a pattern that represents many possibilities in parallel. Gates, quantum operations, are like gentle taps and nudges that choreograph the spins to interfere with one another, canceling wrong answers and reinforcing promising ones. At the end, a measurement is like stopping all the coins and seeing heads or tails. One outcome drawn from that carefully shaped pattern. So the simple version is, build a wave of possibilities, shape it, then read out a result. The shaping is where the power comes from and where the fragility shows up. Here's what actually matters when comparing bits to qubits. With n classical bits, a computer holds one configuration at a time. With n qubits, a device sets up a wave spread across about 2 to the n configurations. It's not free parallelism, you don't get all answers at once, but the wave can be steered so that when it's finally measured, the odds tilt toward a useful answer. That steering is what quantum algorithms are designed to do. To see the flow of a quantum computation, start at the beginning. Qubits are initialized in a simple baseline, often like ready at 0. A gate then puts each qubit into superposition, which means each one behaves like that spinning coin, balanced between 0 and 1. A second kind of gate entangles pairs or groups of qubits, linking their outcomes. From there, a sequence of operations evolves the whole pattern, intentionally creating interference that boosts the right possibilities and damps the wrong ones. Finally, a measurement converts the quantum state into ordinary bits, and the machine reports an answer. Here's a pause to keep it grounded. Measured results are probabilistic. A single run gives one sample. Running a circuit many times builds statistics that reveal the answer with increasing confidence. It's like rolling a loaded die the algorithm designed. Not guaranteed, but biased on purpose. To make this concrete, consider a tiny example, searching for one marked item among 4 possibilities. A classical approach might check items one by one. A quantum approach called Grover's search sets up 2 qubits so all 4 options are present in superposition. An oracle operation flips the sign of the marked option. Think of it like tagging that one possibility so it stands out in the interference that follows. A diffusion operation then acts like a mirror, redistributing amplitude so the tagged option becomes dominant. Measure at the end, and the marked item pops out with very high probability, often in a single iteration for such a small problem. What matters here is the mechanism. The algorithm didn't check each item the usual way. It built a state where all items coexist, then used interference to amplify the one that fits the condition. That's the style of quantum speedup. Not more brute force, but smarter choreography across a landscape of possibilities. Now comes the less glamorous part that decides whether any of this works outside a slide deck. Noise. Qubits lose their quantum behavior when the outside world leaks in. Heat, stray electromagnetic fields, vibrations, imperfect control, Everything tries to peek at or disturb the spinning coins. That process is called decoherence, and it sets a timer on how long a quantum state stays useful. These timers aren't generous. Depending on the technology, coherence might last microseconds to milliseconds, while a useful algorithm could need thousands or millions of operations. Even within that window, each operation has a small chance of error. The errors add up. Put differently, a quantum circuit is like a musical performance where every instrument is delicate, the room is drafty, and the score is long. Without a way to detect and cancel wrong notes on the fly, the melody drifts off-key. This is where quantum error correction enters. The idea is straightforward in spirit and subtle in practice. Take one logical qubit, the qubit that represents the actual information, and spread it across many physical qubits on the chip. Add helper qubits that check for specific error patterns without revealing the information itself. Those checks are called syndrome measurements. If a check reports a problem, the controller applies a correction that nudges the pattern back into alignment. A useful analogy is a choir singing a single note. One voice is fragile, a little cough ruins the pitch. A large choir, with section leaders listening for drift, can hold the note despite individual wobbles. The leaders don't announce the lyrics, they just sense if the sopranos or tenors are sharp or flat and guide them back. In a chip, the helper qubits play the role of those section leaders, listening for errors without reading the lyrics of the data. One of the leading approaches is called the surface code. Picture a grid of qubits arranged on a 2D plane. Some qubits carry data, others perform checks on their neighbors in small patterns. The geometry is vital because it keeps error detection local and scalable. Run those checks rhythmically, decode the patterns they report, and the system can correct many small errors before they snowball. The key idea is that error correction trades quantity for quality. One robust logical qubit might consume hundreds or thousands of physical qubits depending on how clean the hardware is. If each physical gate has, say, a 1 in 1,000 error rate, the surface code can, with enough overhead, push the logical error rate down to something astronomically low, good enough for long computations. That overhead is why discussions about millions of qubits matter. Those counts reflect real protection needs, not just a desire to brag. There's a subtlety worth calling out. Error correction in quantum computing does not copy the data the way classical redundancy does. A strange law of quantum mechanics, no cloning, says unknown quantum states can't be copied perfectly. Instead, the information is distributed across a pattern, and the checks look only for telltale signs of specific errors, like small flips or phase shifts. It's a clever workaround that respects the physics. So how does all of this change what a quantum computer can actually do? Two areas stand out. The first is simulating quantum systems themselves: chemistry, materials, superconductors, catalysts. Classical methods struggle to capture the full complexity of many electron interactions, especially when electrons are correlated in intricate ways. A quantum machine can mirror that behavior more directly, using qubits to represent and evolve the same kinds of states nature uses. The second is a selection of math-heavy problems where interference can be harnessed to find structure faster than classical methods. Shor's algorithm for factoring is the famous example. If implemented at scale on error-corrected hardware, it would threaten widely used cryptography based on factoring. Grover's approach, mentioned earlier, offers a quadratic speedup for unstructured searches, which can be a building block in optimization tasks. Other algorithms blend classical and quantum steps, variational methods, seeking practical value on smaller, noisier devices. Here's an important dose of realism. Quantum advantage is not a blanket promise. Most everyday computing, web browsing, spreadsheets, image editing, won't benefit from qubits. Even for hard problems, classical algorithms and specialized hardware keep improving. Quantum wins where the structure of the problem aligns with the physics. Lots of interacting quantum degrees of freedom, periodicity, or hidden structure that interference can expose, or search landscapes where amplitude amplification helps. With that in mind, it helps to carry a few practical rules of thumb. If a problem naturally looks quantum, like simulating a molecule, there may be a path to real gains. If it requires thousands of perfect operations today, it likely needs error-corrected hardware tomorrow. And if someone claims a dramatic speed-up for a task that classical machines already do well, it's worth asking whether the algorithm truly exploits interference or just runs on a buzzword. A quick tour through the life of a simple quantum circuit will tie the concepts together. Imagine starting with a handful of qubits cooled near absolute zero or trapped by electromagnetic fields. The control system sends precise pulses, microwave for superconducting qubits, lasers for trapped ions, to rotate qubits into superposition. Entangling gates link them, creating a shared state. The algorithm core manipulates the global pattern, phases and amplitudes, so that correct answers become more likely. Throughout this dance, ancillary qubits perform checks in the background if the machine is error-corrected, feeding a classical decoder that decides which small fixes to apply. At the end, measurement collapses the pattern, and a classical computer interprets the results, often repeating the whole process many times to build up confidence in the answer. This is an intricate workflow, and each part is a battleground. Gates need to be precise. Qubits need to be isolated, yet controllable. Measurement has to be accurate and fast. Cooling and vibration isolation are engineering feats in their own right. And the software side, compilers, error decoders, algorithm design, must map abstract math onto the constraints of real hardware. A common misconception deserves a brief correction. Qubits aren't just fancy random bits. A coin toss gives randomness, but it doesn't let two coins interfere with one another. Superposition and entanglement are coherent phenomena, more like waves that can add and cancel. Quantum circuits are designed to choreograph those waves. The randomness shows up at the end, when measurement samples the pattern that was shaped deliberately. Another misconception is that today's devices are already ready for prime time. Demonstrations of quantum supremacy have shown that a quantum device can beat a supercomputer on contrived sampling tasks. That's a milestone, but not the same as useful work. Most practical applications will need fault tolerance, which is the combination of error rates below a threshold and enough error correction overhead to keep logical errors vanishingly rare over long circuits. There's also the scale question. Public estimates for breaking widely used cryptography suggest thousands of logical qubits and long circuits, which could translate to millions of physical qubits using surface codes at realistic error rates. That's a huge engineering project, comparable in ambition to early space programs or the first semiconductor fabs. It's worth noting that not all qubits are built the same way. Superconducting circuits, trapped ions, neutral atoms, photonics, and spin qubits in semiconductors each offer trade-offs in speed, coherence, connectivity, and manufacturing. The field is exploring multiple paths because different qubit types might be better suited to different scales or applications. But the need for error correction spans all of them. Circle back to the analogy to strengthen the mental model. The spinning coin helps visualize superposition, but it misses a crucial element: phase. In quantum states, phase is like the timing of a wave. Two waves in step add. Out of step, they cancel. Algorithms work by setting those timings so the bad answers interfere destructively and the good ones interfere constructively. Entanglement is like linking the timing across coins so their outcomes are coordinated. Error correction is the conductor and the chorus, constantly keeping timing tight despite the noisy concert hall. To keep from drifting into mysticism, a quick reality check. Quantum computers won't replace classical ones. They will sit beside them as accelerators for specific tasks. Most software will still run on CPUs and GPUs. The quantum part kicks in where it earns its keep, and only when the overhead of error correction and control is justified by the payoff. As organizations think about where this fits, a few practical questions help. Does the problem benefit from exploring exponentially many configurations, like in chemistry or certain optimizations? Can a smaller, noisy prototype reveal useful structure today, or is fault tolerance required? How many logical qubits are needed, and what does that imply for physical qubits and facility scale? These are sanity checks that ground expectations in physics and engineering rather than headlines. There's a final, human reason this matters. Entire industries, materials, pharmaceuticals, energy, are built on how molecules behave. Small improvements in catalyst design could save vast amounts of energy. Better batteries might transform transportation and storage. Quantum simulation is a route to understanding these systems with fewer approximations. It won't solve everything, and progress is uneven, but the stakes are substantial. A brief recap to lock in the mental picture. A qubit is like a coin that can spin. A collection of qubits is like a field of waves. Algorithms choreograph those waves so that desirable outcomes build up. Measurement samples the dance and turns it into bits. Noise pushes the system off balance, so error correction spreads information across many qubits and continuously trims away small errors. When all of this lines up, enough qubits, low enough error, smart enough algorithms, the result is a new tool for problems that were out of reach. Put differently, Quantum computing is a bet that precisely controlled fragility can become robust power. It's engineering at the edge of physics. The road to practicality runs through error correction, at scale, with tight control and clever algorithms. The horizon is demanding, but the destination, reliable, problem-focused quantum machines, could be transformative in the niches where they make sense. If this helped clarify the mental model, a like and subscribe helps make more of these.